Okay, let's start. Excuse me. Let's start. It's fine. All right. So, okay. So we have I have covered some part of background cosmology, which means we are describing variables which are average over space, and we looked at their time evolution. Okay. So now this lecture will be very sketchy, and let's see how far we go. Okay, I'll cover. Maybe we'll have more discussion than me lecturing. So we are going to talk about little bit about the perturbations, which means we want to ask, if I include the spatial fluctuations now, how do we do their description? And after that, we will I will spend a little bit of time discussing how we infer the cosmological parameters that we have so far introduced, their values from observed data, particularly using CMB. Okay. So these are the two things I am going to cover. Sorry. Okay. So what we have built up so far is that we use general relativity, the equations of general relativity and the cosmological principle on large scales, and we can set up the equations. So now if we come to slightly lower scales, smaller scales than validity of cosmological principle, then we expect that we will describe the variables, our main variables, which is the metric tensor and the energy density in like this form. Okay. So we have a background only time dependent part, which is the average, and fluctuations about it, and with the expectation that the standard deviation of the fluctuations will be smaller than the zeroth order. Okay. So this is how we can describe. So I am not going to set up those equations, that will take a very long time. I will only tell you about what is the physical content. So by setting this up, I can also, so component by component, I can the material component one by one, we can set up these equations and we can find out their equations. So in general, when I want to describe a realistic universe filled with lots of these materials at these intermediate scales, you will see that the equations are going to be partial differential equations with time evolution as well as partial differential equation. So you can imagine now how difficult it will be to solve. But usually when you solve partial differential equation, one way, how do you solve, one simple way, can you tell me? Separation of variables. Well, here usually we use Fourier transform. Okay. So we will Fourier transform the variables, the row here for example, and we will go to Fourier mode, and for each mode we have an ordinary differential equation. However, the complexity of having the partial differential equation is transferred into having ordinary differential equation for all the modes, and they can couple with each other, different k's can couple with each other. So that is how we solve the equations. G mu nu 0. This 0, it means the zeroth order which does not have any fluctuations, x fluctuations. So all the x dependence is kept in this, in the second term. And so when we set up the equations, you will when you plug these into Einstein equation and the continuity equation for rho, you will get equations for the background equations, background variables first, right? But those background equation variables will enter into the equations for the perturbed terms. So they are coupled equations, so you have to solve them together. So it's fairly complicated, but they are routinely done nowadays. We have developed over the last 30-40 years, fantastic codes have been developed which do all this computation. Okay. So usually we solve by going to Fourier mode, and we solve for each k a large number of k, and how do you decide which range of k do you do? That will be determined by observing the range you are observing. So, the scale over which you are observing, that is the large k, that will tell you the small k limit, and your resolution when you are your resolution of the observation, that small k will tell you what will be the large size, okay, because k and L length, they are inversely proportional, and so that is how we will set up the equations. So, it is a large number of equations. So, just believe me that it is some things are doable, not everything is doable. So, we can do that, and now the physical content. Then if you go to very small scales like if you are going to study the sun, clearly this is not going to work, right, or neutron star, clearly this is not going to work. There you have to do the full solutions using full machinery of Einstein equation, like you must have heard in Bala's lecture yesterday when you do that, or if you study the sun, again there you will be having lots of the electromagnetic interactions and so on, you have to deal with that. Or if you study neutron star, you will have to deal with these strong forces will come in because the density is very high, and so those. So, depending on your physical system, the scale, what force will be dominant, you have to deal with that. So, that is the broad picture. Yes. So, I will explain this part, what I mean by primordial. Okay. So, for us we are tracking CMB temperature and the energy density on larger scales. So, we the question now is what created those fluctuations, what created the CMB fluctuations we see today, and the material fluctuations we see today. And yesterday I said that the two, we can link the two, because same physical origin, and it is an economy of the theoretical modeling, and is it justified by observational data? That is what we ask. And now at this stage, without saying what has created, so you have to, even if you take the CMB today, you go back and back in the past, the fluctuations have to be there at some point. Without those, it cannot be created, because to create the fluctuation you have to input energy from somewhere, right, some stirring up has to happen. And if the universe is a closed system, all of these components together is a closed system, then there is no possibility that that can happen. Maybe if you think of extra dimension and 3D, 3+1 interacting with another dimension, you can think of such exotic models. But if not, there has to be some fluctuation in the materials at some initial time. This Ti, what I mean is not the components, but some initial time, okay, very early. So, some fluctuation should have been there, and from there it was created and the photons travel, but in between if they interact with matter and so on, all that information has to also be there, and we have to set up the equations for this, and this is doable. So, for CMB this is how we do. So, some primordial fluctuation, this is what I am calling as primordial. I do not know what the origin is, but it should have been there at some point early in the history of the universe for us to see these fluctuations today. Similarly, likewise, the energy density, that should have been the same fluctuations, we can assume it was there, which is perturbing both. So, in this region, if there is more matter particles, maybe photons are also more, okay. And so that the two of them, high density means high density both in photons as well as materials. You can also imagine fluctuations which is different, of course. You can imagine maybe here there are lots of photons, but there are not so many particles, matter particles, that also you can. And then the curvature caused by the photons and the curvature caused by the other, maybe they will cancel out, okay, under density and high density eventually. So, that kind of gravitational potential is also possible, and that is called isocurvature. The curvature remains same. The one I am describing here is where if there is more matter, there are more photons also. They track each other, and those are called the adiabatic perturbations, and that is what I am. So these two kinds of perturbations, there is a way to test them in the observed data, and what the observed data says is that this is the adiabatic one is what is. So the picture you should build in your mind is where if there are more photons, there are more particles, and that is all originating from this primordial fluctuation. So at the moment I do not know what it is, okay, but it should have been there. But from that primordial time, of course, the photons will have a different evolution, because they stopped interacting with matter at some point and they just nicely cooled down. Whereas the rho, gravity is going to pull the nearby objects and so on, and so the clustering will happen, and on large scale I think places will become empty, and the highly clustered regions will become even more highly clustered. Okay. So this is the picture we have, and so when we look at the CMB data and the matter distribution today, like all the data that I showed you, they have imprint of all of this, okay, primordial as well as. So an important goal of the science or cosmology that we do today is to look at the data and can we say something about what happened, what is this interaction like, what is this primordial like. So this is one of our goals to find out, and that is what we mean by understanding the universe, what happened. Okay, so I think I have, yeah. So now let us come to the origin of the primordial fluctuations. Yes. Yeah. How these two?
Yeah, like how are they different?
This is how are they different? Okay. They because I have written expansion gravity scattering together, same. Okay. I just use the same words, but what I explained just now is that their interactions are different. So the photons will interact till the last scattering. So photons will be usually, if you look in the books, you will find it described as a fluid of photons, and just before decoupling I already explained yesterday, before they became free, they will be scattering of hydrogen electrons, a lot of scattering will happen. But as the universe expands and the photons lose energy, the rate of scattering will decrease. So the scattering there can be modeled as Thomson scattering, and you can write down the scattering cross section, and that will enter in this scattering is what I mean by that. And the expansion is the expansion of space that will also affect how it behaves, and the gravity here, of course, this whole couple equation, and the gravitational forces potential will enter. So that is what we mean for the CMB. For the matter is different. For the matter it will be gravity will be different, no? It will be actual gravitational pull, depending on the scale, clustering will be happening. Expansion is similar, it will again be coupled equation, it will enter. Scattering, maybe some scattering happens depending on how you model. So if it is like dust particle, if galaxies or dark matter is modeled as dust particles without any pressure, then the scatterings and so on will be 0, it will not matter. But if there are some interactions, let us say, I do not know, there are exotic models are there where dark matter is modeled as some particles which can interact weakly with various things, then you will add those cross sections here. Yeah, depending on your model. So this is a very general thing I have written, because you have to write down for specific models, but they are different, these two are different. Sorry. Okay. So let us spend a little bit of time thinking about what could have caused the fluctuations, the primordial phi at time Ti. So yesterday we briefly talked about this, why CMB photons in different directions have very similar temperature, because similar temperature happens when regions are in statistical equilibrium, but they are coming from different directions, and how could they have been in statistical equilibrium? That is one question, and the second is of course what gave rise to these the fluctuation, primordial fluctuations. And so we usually use the word seed for structure formation. Structure means the large scale structure, the filaments and nodes and so on. So they form the seeds. Okay. So these two, the best answer we have currently, I would not call it the definitive answer, because we do not have, it is just a model which describes very well, but we do not have definitive proof of that this is exactly what happened, and that is the story of inflation. Okay. So to understand, so inflation basically by definition, it is just a period of accelerated expansion in the very early universe. Okay. Very early means like before nucleosynthesis, where the atom, not atoms, but protons and so on were condensed to form those particles before that. So this, if this such a period happened, then what it says is, so when we are describing cosmology, we have two rates of change. That is what I have written here. There are two things we have to take care of. One is that there is finite speed of light, and because of that, any region which is causally connected will have a finite size at any given time. Okay. Because when I say interaction, causal connection, it means I am sending a signal, a photon, and that is the fastest speed I can send, and that is received, and that gives me the causally connected size at any given time, starting from some initial time. Okay, the distance that the photon would have traveled. So that is finite, but of course it increases with time, because the photon is traveling, as time goes more, photon is traveling more. So that is finite, and we also have the rate of expansion of space, and so it is a competition between these two. We have to take these two into account. So what inflation says is, suppose before inflation there was a small region of space where it is, you can imagine thermal equilibrium. Okay. I should be careful, it is okay, it is in equilibrium. Okay. And because the causal, they are within causal horizon, and if suddenly it expands very fast, okay, so from this size it has become very fast, very large, like this picture is depicting that a small region become this big region as you go in time, in a short time. Then when you go from here to here, the region which was in causal contact has now been blown up to a bigger size, and you may think, if you did not know that such a thing happened, you will think that, oh, they should not have been in causal contact, just by following this speed of light, how the causal connection happens. Okay. So in this way it sort of explains a region, that means the photons which are coming from here and the photons which are coming from here, actually a little bit of angle here also, there is some causal size, about 1 degree size, they were actually in causal contact, and inflation expanded them very rapidly, and today we think because of the finite speed of light, it seems as if they were not in causal contact. So it resolves that issue. Okay. That is one thing, that is about the background. The second point is, the second important point is about the fluctuations. What gives rise to these fluctuations, and that briefly we discussed yesterday. So to ask that question now, the next question you have to ask is, what kind of energy density filling the space can give rise to inflation? So in the morning we studied a universe filled with radiation. It gave rise to a scale factor which is 1/2, T to the power 1/2, and or only galaxies, baryonic matter not interacting. If that universe is filled with that, we saw t to the power 2 by 3, those are not accelerating. So, if the universe is filled with what we know as ordinary matter or light, it is not possible. So, it is not possible. So, it was realized by in the early maybe 1979 or to 1984, around that time. Maybe Linde was the one who built a proper model, sorry, fluctuations, let me remember, maybe Mukhanov and what is his name? Okay, I forgot the paper who first worked out the fluctuations. Okay, so it was realized that if the universe is actually filled with some scalar field, quantum scalar field, then you will write down the scalar field, you will write down a Lagrangian, you will write down its energy density, its pressure and so on, and you will be able to find that if it is like if the evolution of the scalar field is like it is rolling down a hill. Okay, I am not going into the detail, I am just giving you like a storytelling. Okay. So, if that is so, then it is possible to give rise to inflation. The conditions required for inflation are satisfied and you can have this. So, that was there. Yeah, so that was given by a lot of people. Alan Guth was there, Starobinsky was there. There are other people, Steinhardt and so on. They developed that. Then Mukhanov and this, I forgot the other author, they looked at the quantum fluctuations. Okay. You take a scalar field and then you take the quantum fluctuations, and they studied the properties of the fluctuation, and they computed what is usually called the power spectrum. I will just explain to you what a power spectrum is. So, they calculated what a power spectrum is, and they said this can give rise to the fluctuations. So, you have quantum fluctuations, and then from that they turn into particles that we are familiar with. So, the universe emerges from that epoch as a space where there is gravitational potential well fluctuating from place to place. Okay. So, that is the picture we have. So, I will tell you a little bit about the power spectrum in a bit. Okay. So, this is the fluctuations get imprinted, and this is the now sort of the picture that we have, which best explains the what we are seeing in CMB and matter distribution. Yeah. Usually we do not talk about equilibrium in that for the fields, but the picture is that, yes. Yeah.
So they decay into photons?
They decay into photons and fermions and
so those are
standard model particles. Yeah. Okay, so this is the very storytelling way of introducing inflation to you. I hope you all will do a proper course and learn it properly. Now, so now I will come to the power spectrum. Okay. So this is the whatever I said in words, this is now the pictorially. So we have primordial fluctuations, and these numbers are the colors are representing the different values from place to place, and then the CMB will have its own evolution. These two, matter and CMB, will be coupled up to some time. They will be interacting a lot, and then once decoupling happens, CMB will evolve into what we see today, matter will evolve into what we see today. This is the evolution. Now, the point I want to make at this stage is, we measure this. Okay. Now, can we compare this from here? Can we track in each direction the CMB temperature back and say that, okay, in that region, this is the fluctuation value that it arose from. Is it possible to do that? So we are modeling all the things that happen in between, but you can't track photon by photon, right? What happened to it? So there are things that happen like CMB lensing. The photons also get lensed because in this epoch, the CMB photons are traversing through this. They are all going in all directions. When they hit potential wells, they are lensed, and that is also imprinted in what we see today. So a lot of these interactions that have happened, we cannot track. So when we want to compare theory and observation, that means that we cannot make a simulation and say I am comparing my CMB with this. What you have to do is you have to construct some statistical quantity out of the data, take some statistical quantity out of the theoretical simulation data, and that is what you compare. And what we compare today, most of the 90% of the cosmological information that we have had comes from the power spectrum. Okay. So the power spectrum. So here I am writing out the primordial power spectrum. So let me tell you what that is. So power spectrum is okay. I have to digress a little bit into random fields. Okay. Okay. So you are familiar with random variables. So a random variable is something which maybe you can measure many times, and you have depending on how many times you measure, you have values for that, and you look at its properties. Whereas a random field, which is relevant for our cosmology analysis, is something which is, you have a manifold, and on that manifold at every point you have a variable, which is a random variable. Okay. So your field is f as a function of x vector, but this is a fluctuating quantity. From at that point fluctuates depending on what you are doing, measuring and so on. It's a fluctuating quantity, it's a random variable. Then you may ask, f at x vector prime, are they correlated? So how will you do that? You will measure their correlation function very simply. This is the ensemble expectation. Now we have the CMB here. Do you think they are correlated? So in the CMB case, we have a direction. Instead of x, I have my direction. So in this direction and slightly next to that direction, they are correlated in that picture, right? If it is blue here, the neighboring is likely to be blue up to some range, and beyond that it dies out. So the correlation dies out. And so this is the usual 2-point correlation function. So now I said that usually when we solve theoretically when we study the fluctuations, we go to Fourier space. Okay. So I will have f of k, f tilde of k vector. So this is not. So when you have a function and you take the Fourier transform and you construct the quantity f tilde of k mod square, this is called a power spectrum. Okay, this is in signal processing, you would have learned this. Okay. So this is the quantity, basically essentially this is the quantity that we use for doing all the data analysis at the most basic level. I will tell you how we are going to go beyond that. Okay, so from the theory, from here, from the theory side, theoretically what we compute when we calculate inflation, for example, write down all the equations for inflation, we will predict the power spectrum. That is what you calculate. Okay. So you would have calculated correlated function. If you had some maybe a basic course in quantum field theory, you would have calculated some Green's functions and so on, right, 2-point correlation functions, and that is what is giving rise to the power spectrum. So the theory will predict that, and what is written here is I have removed some k powers which are related with the dimensionality, and this is what is called the power spectrum. But you will see that there are 3, so there is a power spectral index ns, there is an amplitude, and there is a k0 here. So here the powers are, the variables are ns and a, these are the variable, cosmological variable, it will go into cosmology. This is something I choose. So this is a power law form which is nearly scale invariant. If ns is very close to 1, if it is 1, this is independent of k, it is a constant function in k. So if ns is slightly less than 1, it will have a tilt like this, and so it is telling you the spectral index. And this k0 is something, based on my experiment I will choose a convenient place where I can mark what is the amplitude at that k. Okay. So usually we will choose this as k in length scale 0.05 megaparsec inverse. Okay. So that is convention. So from the experiments we choose that. So, but you will ask, why is it this form? Why are we using this? So from the theory, depending on what your inflaton is and so on, you will have all kinds of power spectrum. Okay. But we are having this because when we fit with the data, so I am using going back and forth, so it is not a linear storytelling I am doing. If you fit with the data tells that it should be of this form, and ns is very close to 1, and a is like 10 to the power minus 9. Okay. So that is what, so these two at the moment just take a and ns as free parameters which will go into the data analysis. Okay. So this is the power, this is the primordial power spectrum, which this can be computed actually from inflation. When you are doing inflation, scalar field inflation theory and so on, you can compute this. You can compute ns and a as dependent on what the field is doing, the field velocity, field value, all those will enter, you can compute this. Okay. Okay. So that is the power spectrum. Now the next thing is, now what is the standard model? So now we know what the primordial parameters are. What we mean by the standard model of cosmology? So in the standard model of cosmology, let's introduce the parameters. So I just introduced a and ns, and we have these as the parameters. We talked about this in the morning. I don't have gamma here, photons, because they are very small. Okay, they have dropped because of that a to the power 4 minus 4, it has dropped and it is not very important. Okay, but I have a new variable here, tau, and I will explain that after I finish this. Okay. So tau is related to the epoch of reionization, and I will explain it a little bit later. So these are free parameters which cannot be determined by the equations, because we are solving say ordinary differential equations. We need to give initial conditions, which in our case is last condition, today condition, and we travel back, we look back, solve the equations back in time. So their values we need to, these of course they are not, they are primordial, so they are not today, but the omegas are the values today. So these go in as inputs. So now how am I going to read out their inputs from observation? That is the question I am going to look at. Okay. So for that I'll use the example of CMB. So if I have CMB temperature fluctuation measured, observed data, then what I do is I will also do split it into angular power spectrum. I will also calculate what is called a power spectrum from the data. So I have the data, you have seen the CMB data value different. Then what we do is we do harmonic transform, spherical harmonics, okay. And we can from this, given the left hand side, you can invert and you can obtain ALM, right. So that is very trivial to do, and by the ALMs, now from the ALM you will average over all the M's for each L. So I have for each L, I have 2L plus 1 modes, right, M modes. So I am dividing by 2L plus 1. Oh, sorry, this is a mistake, this is M. So I sum over all M's, ALM mod square. Why am I taking mod square? Because it is a complex quantity, I want a real number. So I will compute this. Then for the purpose of plotting, we will typically we will plot L into L plus 1 into CL, okay. So this we can compute from the data. So from the data, this is what we get, no, these dots, the dots are what we are getting, and the theory, the red part I will tell you just now. So now that is what the data is saying. Now from the theory we want to compute CL, not analytically, but we will set up the equations like what I described, the fluctuation equations. Then for the CMB, suitable for the CMB, we will set up the equations, and actually the equation simplifies to, the solution simplifies to this form. So I am showing it to you without proof, okay, please read it up on your own. So here let me explain what these terms are. Matter is easier because matter power spectrum is directly Fourier transform. CMB is a little bit more complicated because CMB from space you are converting into angle, okay. So the calculations and the variable transformations are a little bit more complicated, but not too complicated. So there are two terms entering here. This is the primordial power spectrum, I already explained to you. What is this? This is usually called the transfer function, and this contains the information of the interactions that the CMB photon had from very early epoch before decoupling till today. So this is what I showed in the previous slide. Temperature is given by time integral over scattering blah blah times primordial, okay. So that is contained here. So this again you will have these days there are lots of nice codes which will compute this for you and give it. If you are very daring, you can also set up the codes, write codes for this, but that will be reinventing the wheel. So you can, it's nice to look at this function, what does it look like. Okay, so now where are these parameters going to go in, right? So this is going to be a function of A and Ns. This is going to be function of all these other 4 parameters will enter here, okay. So this will be a function. So that means for if I choose a set of values for this, I am a theoretician, so I can choose any and solve my equation. If I do that, this will have some functional form, but if I change it, then it will have a different functional form, so it will look different. So now you know what I am after. What I am going to do is, I am going to take these values and say, okay, reasonable, maybe each of these is in some range for each one of them. So for omegas, maybe I will say 0 to 1, 0 to 1, because they are fractions, right? And I will use that as my sort of a prior, I will plug it in, I will vary them and plot different angular power spectrum CL theoretically. Similarly for A and NS, I will put different range of values and plot this theoretically, and I will compare with the data. So let us see the comparison. So here the blue dots are the data, right. Now the red dot here, if I change my variables, I am going to get different curves. So what is done here is to get the best fit. What is the set of parameter values which fits? So you can see what a good fit this is. You have found the set. and those values are, those are the fractions which are given here. This is from Planck and these are the values. So, A is supposed to be 10 to the power minus 9, NS is 0.98 and the fractions of the lambda, dark matter, baryons, they are given here. Okay, so this is how we determine these cosmological values. But I have not told you about tau, the epoch of reionization, which I will come to later. So yesterday you were asking about what more can you do with the CMB. So you can see how good the fit is. So now the question is, why are we limited at 2500? Any suggestions for why we are stopping at 2500? We don't have enough resolution. Yeah. Yeah. So this is because Planck resolution is 5 arc-minute, and that tells you basically up to what L you can go. So if you design new experiments which can go to smaller angular resolution, you can get this, and you can extend this. But till here already the error bars are very small, no? So, but there is still some instrumental noise that can be improved, and some experiments are being designed, and one is underway, which is the Simons Observatory, and that is supposed to go to all the way up to some 5000. And if we know that, so all these numbers that I have quoted, I have not put the error bars, there are error bars. So the purpose of precision cosmology is we want to shrink the error bars and know them as much as possible. And what is the purpose of doing that? The purpose of that is these values will go back and tell us this inflation model is correct, this is wrong, and so on. Okay, or inflation is incorrect also, maybe something can happen. So we are going to know more about those. Yeah.
What is the difference between dark matter and dark energy?
I have not told anything about dark energy, but this dark energy is the in the morning I introduced rho lambda, right, cosmological constant. So that fraction is this. Yeah. So it is saying that that has the largest fraction. Okay. So at this point now you should be asking, this is power spectrum is basically 2-point function, right? I take two factors of the field and I take their ensemble, multiply them ensemble expectation by multiplying at different spatial locations. That is what I have written here. See, x, I am sorry it is not going, x and x prime, they are two different points, and I am asking how they are correlated. And as I vary the angle, I am finding out how they are correlated. But you know, yesterday I mentioned that when we do statistical analysis given that CMB data, there are many things you can do. 2-point is like the simplest. So if the field is Gaussian, if the CMB is Gaussian, then the 2-point function contains all the information, the entire probability distribution you know by this measurement. So you do not have to do anything more. But if it is non-Gaussian and we find out what type of non-Gaussianity it is, I mean is it skewed this way, that this way, kurtosis and so on, then we will be able to go back and select the inflation model which is correct. So that is why we really need to shrink the errors, all these errors have to be shrunken to get that information better. Okay, so this is about the CMB. Yeah, him first.
Why are the error bars for low L modes so much more higher than?
Yes, very good question. So this is something called the cosmic variance, it is coming from something called cosmic variance. So let me explain. If we go back to the L, we are averaging over, so when for low L I have only few L's, right? And so I am averaging over very few modes. So that causes it's a fundamental limit of our putting the data in this form. Yeah. Okay.
Yeah, even I wanted to ask the same.
Okay. So you answered, right? Okay. Yeah,
I have a question.
yeah.
Why is there like a sharp peak between the 30 and 500?
That is just they wanted to include everything. So, these are the large scale modes. So, roughly 1 degree L to degree separation, 1 degree is here. So, because these are the large scale modes. So, the physics is slightly different because if I go a little bit deeper into the CMB physics, the causal horizon at CMB decoupling corresponds to about 1.7 degree from our view today. If I look back, it will project that. So, those modes which are outside, they all come here, and the modes which are inside that 1 degree, they all of these are. So, here these are the ones which are doing a lot of scattering and blah blah, all those physics is happening. These are more primordial. Okay, so they are coming from correlations of 2 photons which are actually not in causal contact at the time of the decoupling. They are far away from each other, and so this is so. When we use this data, these will tell us about the more information about the primordial physics. Though this also contains information. For example, this NS from the integral form, you know this, if this NS, this tilt is very deep, is not 0.96 but 0.9, then these are going to dip, right, because in the integral it is sharply going down. So, they affect there also, but there is a strong effect here. Unfortunately, the error bar is very high here. That is the, so you guys can be, if you have bright ideas about getting over cosmic variance, if you devise some new way to divide and cancel out cosmic variance, that will be fantastic. Okay. So, there are people who are trying it, very smart people, but if your young ideas come up, it will be very useful to the analysis. Okay. So, now what is the future of the analysis? The future of the analysis is to go beyond 2-point function, because 2-point function is really true only for Gaussian. So, for the non-Gaussianity you have to go beyond, and what do people do? You can calculate 3-point function, okay, or 4-point function, and so on. So, I think in the literature, I think people are actively using up to 4-point function. The calculation becomes much harder if you go to 4-point function, because on the sky you are going to correlate 3 points, and you are going to take any combination of 3 points and add sum over, average over. Okay. The ensemble, one point I should mention is ensemble expectation is replaced here by spatial sky averages. Why? How can you do that? Any thoughts? Why? When you have a random variable, ensemble expectation means you have many realizations and then you average. Here the random variable is at one point, at another point there is another random variable, and it is, and I am correlating and replacing the ensemble expectation for that point to the spatial average. So, have you in, that's not enough. One word which you have learnt in statistical physics. No. Have you learned the word ergodicity? So, ergodicity is saying that, let's look at the same. I don't have many slides, so we can spend more time talking. Right? Okay. Yeah. So, yeah, what did I want to say? I have to go back. I wanted to take you to the CMB. Yeah. So, ergodicity. So, here it's a very important, again this is an assumption, okay. We are assuming ergodicity to do all this data analysis, but usually people don't mention it. So, it's good that I mention it to you. So, the random variable at each point, it's a random variable, but when we make a measurement, I have only one number. So, I don't have ensemble expectation. Ensemble expectation means I should be able to realize it like infinite number of times and average. I can't do that. So, the only way is to assume ergodicity and say the random variable here and random variable at any point, they are identical variables, and all the ensemble, in the ensemble there will be a range of values the random variable can take. At least once it will be realized in the other locations, okay, and that is what allows us to do to replace ergodic ensemble averages by spatial averages. And in cosmology you will do it all the time. For the matter distribution also, you will be replacing ensemble expectations by this.
How will you carry out this average check? Isn't it at single x and single x prime?
No. Yeah. So, I put this ensemble here, this bracket here. So, it means I take x and x prime, okay, a pair. Then I am also going to use, so the distance between them is, let us call it small r, okay. So, I fix that, and if I also assume that the data is homogeneous and isotropic, particularly isotropic, then if I take this pair, I rotate, I shift, I take another two pairs with the same distance, maybe rotated and shifted. Then that pair is, I take that pair also, I take all possible two pairs. All of that I construct and then I average, and that is how this ensemble is calculated. By definition, this is the ensemble. However, in practice, we are replacing this by spatial average. So, we are assuming homogeneity in isotropy when we say it depends only on the distance between those 2 points. That is why in the CMB it is the angle, no? Angular separation, you plot that on the x axis. In fact, that is a nice, I do not have that plot, it is also nice to see that. So, you have theta, the angular separation here, and you can find a correlation as a function of theta. So, it looks like this. Yeah, there is a peak here. So, there is a peak at around theta equal to 0.7 degrees, and at most you can go to maybe 90 degrees. So, the neighboring points are likely to be highly correlated, so that is why it goes up, and then there is a bump here, and this is the 0.7 degree that I talked about. So, there is an excess correlation at that point. So, I did not go explain this very well, but this is what it looks like, and when you take the Fourier transform of this, you will get that power spectrum. Okay, so the future is to go beyond power spectrum. So, if you guys get into this area, learn how to go beyond power spectrum. Okay. So, a lot of my research work is done on going beyond power spectrum by looking at the field. Where am I? So, I look at this CMB field, for example, or matter field, and instead of doing endpoint from 3 point, 4 point and so on, I look at the subsets where the field values are higher than the range, okay, level. So, it is called level set, and I look at their geometrical and topological properties, and because those properties will depend on if, for example, omega matter is more, then maybe there will be more clustering, and so fluctuations will be fewer. Or dark energy is more. If dark energy is more, then things would have expanded and so on, and so the clustering will be different. So, that way it will show up in those statistical quantities, and I design those statistical methods for comparing data. Okay, so now let us go beyond now to the frontiers, what things that we are looking for and we do not know, just to complete the story. Okay, so one thing we are now looking at, this is a very biased selective selection of topics that I am biased to. Okay, so there are many topics in cosmology that you need to study, but just indulge with me. So, one of the frontiers is primordial gravitational waves. So, I discussed the 2-point correlation primordial power spectrum, that is the scalar power spectrum. So, in the metric tensor G mu nu in the primordial field, the G mu nu, you have seen the G00 component and the Gii component as 1 plus phi. You remember when I related it to Newtonian physics, I wrote it like that. Okay. So, that is a scalar quantity. So, G mu nu, even though G mu nu is a tensor, the perturbations you can write as eta mu nu plus some term. So, that term will be there for every component, but those components you can split into some which are vectorial, some which are truly tensorial, and some which are scalars. Okay. For example, G0I, the perturbations there, they will transform as a vector. So, like that you can do, and gravitational waves will be the truly tensor part. Okay. So, what I described till now is only the scalar perturbations, but there should be the primordial gravitational waves also. Because of the density fluctuations, the gravitational waves should have been present in the early universe, and if that is there, how will it show up in the CMB data is the question. And the way it will show up is through CMB polarization. Okay. Polarization of CMB is caused by breaking of isotropy, and when gravitational waves are present in the space, it is, or things are oscillating 90 degree and then in a quadrupolar fashion, it will generate an isotropy, and that will lead to CMB polarization. So, that is something we have not detected till now. So, that you will know it in the literature as CMB B modes. So, that is a very exciting thing. If whoever finds it will get Nobel Prize, I am pretty sure. So, that is one goal. The second thing that is very exciting is the epoch of reionization. So, we have so far I have described only the big epochs, matter decoupling, then radiation domination and so on. But if I look after decoupling, so the decoupling happened somewhere here, this is time going this way, then after decoupling most of the universe was hydrogen. Okay. So, then because they are clustering due to gravity, they will start clustering, and here at some epoch first star will form, and when that star forms it will emit light and it will ionize the region around it, the hydrogen around it. Okay. So, then it starts the epoch of reionization. For example, Saurabh here is trying to find signal from here, the global signal corresponding to the CMB average temperature. So, Saurabh and Mayuri, they are trying to find the signal from here. Okay. Now, what is the signal? Okay. So, this hydrogen, all this, there is so much hydrogen, the entire universe is filled mostly of hydrogen. There will be some free electrons because not everything will combine. So, the hydrogen, there is the transition called 21 centimeter, I am sure you all know about it now. So, that is the hyperfine splitting of energy in the ground state itself between the spin being aligned up and down, up down. So, that the wavelength is in the 21 centimeter, and that emission is expected to be, it is a very low probability signal. Okay, it is a forbidden line actually. However, the amount of hydrogen and the amount of time we have is a lot. So, because of that, there is hope that we will detect the signal. But the signal from here, these dark ages before stars formed, they would have, in this intervening period, they would have redshifted to very high wavelengths. So, we do not have, we have detectors down to what, FM radio and megahertz, that is what we can build, right. But if they are redshifted beyond those, then at least with the current technology we do not have hope of detecting them. But somewhere here towards here the age is just right, so that we can start seeing, our detectors can start seeing. So, we expect to see the redshifted 21 centimeter coming from this epoch, okay, from this. Then when the stars form, it will reionize. The reionize means ionize the hydrogen, and so that means when hydrogen is ionized, there will be lot of free electrons again available, right? Now CMB photons are traveling through this, they are coming to us through this, and so when they encounter those photons, CMB photons will get scattered again, and that effect is what I wrote as tau in the cosmological parameters. Okay, that is the optical depth in this epoch. So as more stars form, you can see this, the picture is depicting more stars and then galaxies and so on forming, and they will ionize everything, and everything will be ionized at some stage. So those of you who are working with JWST yesterday, a lot of you were saying, early epoch, you are probably probing, you are looking at galaxies which are coming from this epoch. Okay. So now I think JWST has seen redshift 12, so this is happening between redshift 30 to 6, around that epoch. Okay. So JWST is looking at it, and there are lots of experiments which are designed to directly capture the 21 centimeter signal. It's very hard to detect because our galaxy emits in that frequency a lot. Yesterday I mentioned the synchrotron radiation, and that is the major source of foreground which is causing confusion for us. Okay, so that is the okay, sorry, sorry. Okay, so I have already told this. So now let me go to the dark matter and dark energy. We don't know what they are, so all of you are welcome to find out what they are. Now last slide for before inflation, what happened? So we are pushing our ignorance further and further in the past. Just like theoretically, we are pushing our ignorance more and more now into symmetries. What are the symmetries that nature respects, nature follows? So before inflation, so we said, okay, inflation, there was a quantum field and it produced all these fluctuations. But what about before that? What is Big Bang? What is the meaning of the Big Bang? Physics makes sense. Physics makes sense up to, okay, I have this much space. In the past I am shrinking and pushing all the, so in the little, very small space I have so much energy density. So that means that our laws of physics that we are familiar with, they will break down, right? And that is basically, I mean, we understand till that. We understand till maybe inflationary, we can say up to inflation. So Planck scale is where, you know, gravity and everything. So, so there's a lot of research going on here. We understand up to that epoch, but beyond that we don't know. So again, those of you who are theoretically inclined, you can work on quantum gravity, string theory, and so on. Okay, I'll end here. My throat is hurting. Okay. Questions? So I gave a very selective set of topics, okay. So for example, I didn't touch anything about nucleosynthesis, how the first elements form and so on. Maybe I'll ask Biman to cover it a bit. No more questions? Okay, let's go for tea and we can chat there.
Tea opens up their mind.
Huh?
Tea opens up their mind.
Opens up your mind, yeah. I need some hot. I have water, but it's scratching.
Yeah, probably.